Welcome back, friends. This is the fifth video of the lecture series group action, and here I wanted to prove about Cayley's generalized Cayley's theorem. For that I wanted to use a left regular action. So in a group action language I wanted to prove generalized Cayley's theorem and obtain the regular Cayley's theorem, which is simpler version of finite. Okay, let's do that. Left regular action. Let us review left regular action. What is left regular action? When G and G is a group and G acts on itself by this just Gx. Okay, and in a second video I mentioned about this kernel stabilizer and the kernel relation, that is I am going to use here. People should see this video one by one to understand this lecture, because it's a series. It's not a random video, it's a series. Okay, so you have to see the second video to understand this. Okay, let's see, let's calculate. So I said that giving group action on a set is same as is a kind of giving a permutation representation to Sx. So I wanted to calculate the kernel of the homomorphism is same as the kernel of the action. Kernel of the action is nothing but this is a set G belongs to G, such that see, I gave a action, so that I will get a homomorphism from here to here, group homomorphism. So I have a G, that means this homomorphism G acting on X, the homomorphism G equal to ID on X, and that is also G in our case. That is G belongs to G, such that like this phi G of X equal to X, that is nothing but set of all G belongs to G, such that G comma X equal to X. I am writing one by one. Set of all G belongs to G, Gx equal to X. Now if you multiply by X inverse on this both sides, what you will get? G belongs to G, G equal to identity, that is nothing but identity only. So in this particular action, the left regular action, the permutation representation what we are getting from G to S of G, S of X, here X also G, okay, is injective. That is what we saw, right? Here the ID map is identity. Okay, that is what we saw here totally. So that means group is sitting inside here, isomorphic copy. Okay, so this is called the generalized Cayley's theorem. Generalized Cayley's theorem. Okay, theorem generalize. Okay, generalized Cayley's theorem. If G is any group, G is a group, any group, infinite, finite, then G is isomorphic to the subgroup of SG. Let's do it in the finite case. Suppose to obtain the regular, suppose G is finite, let's say n, then this SG is nothing but Sn, is permutation on S symbols. That means G is inside Sn. So this is a regular theorem, right? Cayley's theorem. Okay, what is saying that G, let G be a finite group, then G is isomorphic, let's of order n, isomorphic to some subgroup of Sn. Okay, I wanted to also say the limitations. For example, Let's take a G equal to S3, which is order 6. So S3 can be thrown inside S3 because that's the same thing. But according to this theorem, S3 should go to S3 factorial. Okay. S3 factorial is nothing but, the order of S3 factorial is nothing but 3 factorial factorial. Okay. So it's huge. So the idea is you sum of the group, you cannot go further, like Z4 can throw inside S4 by Cayley's theorem, but Z4 cannot go into S3 or S2 or even S1 because it cannot, because order 1, order 2, this is order 6, 4 does not divide 6, Lagrange's theorem. Okay, I also posted another video about Q8. Q8 we can go inside S8, this is by Cayley's theorem, but Q8 cannot go inside Sk where k less than or equal to 7. This is uses a very beautiful and interesting group theoretical fact, group action fact, which I already posted in English version. So you just go and see and make use of it.